I want you to close your eyes for a second. I want you to try and visualize nothing. And I don't mean a dark room. I don't mean the emptiness of space between stars, because even that has distance.
Yeah.
Right. It has dimensions.
It has a here and a there.
Exactly. It has properties. I'm talking about a state of absolute total void. No time, no space, no matter.
Not even darkness.
No darkness, even, because darkness is just a property of light, and there's no light.
It is surprisingly difficult, isn't it? The human brain isn't wired to process true non-existence.
It's impossible.
We always try to put a border around it. We imagine a black box, but if you have a box, you have something.
Exactly.
Yeah.
It makes my head hurt if I think about it too long. It's like trying to visualize a color you've never seen.
Yeah.
But here's the thing that really keeps me up at night. The prevailing theory of cosmology. The smartest people in the room using the most advanced math we have suggests that everything we see, from the coffee in my mug to the Andromeda Galaxy, somehow popped out of that state.
It is the ultimate free lunch. You start with zero and you end up with, well, with a universe.
And that is the mission of today's Deep Dives. We are tackling the heaviest question there is, based on the research from space dust. The question is simply, how did everything start from nothing?
A small one to start the day with.
Just a light topic. And I have to be honest, when I first looked at the packet for this, I thought we were going to be talking about philosophy or, religion. But we aren't, are we?
No, we are firmly in the realm of physics today. But it is a weird kind of physics.
How so?
It's the intersection where the very small meets the very large. To understand the Big Bang, which is the biggest event in history, you have to understand particle physics, which is the study of the tiniest things in existence.
That feels counterintuitive. If I want to understand a skyscraper, I don't usually start by looking at the molecular structure of the rivets.
I get that. But in this case, you have to. Because 13.8 billion years ago, the entire skyscraper was squeezed into a space smaller than a rivet.
Wow.
So the rules of the tiny quantum mechanics were the rules of the whole universe.
Okay, so we are crashing these two massive fields together, particle physics and cosmology. And this source material lays out a bit of a roadmap for us. We need to understand the ingredients, what the universe is actually made of.
The building blocks.
And then we need to understand the mechanism. How do you get something from nothing?
And that mechanism is the key, because the headline here is that nothing isn't what you think it is.
Right. Space dust implies that nothing might actually be something.
Yeah.
But we are getting ahead of ourselves.
We are.
Before we can understand the explosion, I feel like we need to look at the shrapnel. If the Big Bang was a crime scene, the particles we see today are the clues left scattered everywhere.
That's a great analogy.
So let's open the pantry.
Mm-hmm.
What is the universe baking with? We call this the standard model.
The standard model, it is essentially the periodic table, but for the stuff inside the periodic table.
Yeah.
You know, in school you learn about protons, neutrons, and electrons. And for most of history, we thought that was it. We thought the proton was a solid ball, like a tiny, tiny marble.
A fundamental building block, indivisible. The word atom itself means uncuttable.
Right. But then, in the mid-20th century, we started smashing things together at high speeds, and we realized that the marble cracked.
It wasn't solid.
The proton isn't a solid ball. It's a bag of even smaller marbles.
This is where we get to the fermions. These are the bricks of reality, as you said. And inside the fermions, we have the quarks. I have to stop here because quark is arguably the best name in science.
It really is. It comes from James Joyce's book, Finnegan's Wake.
I didn't know that.
Yeah, the line is 3 quarks for muster mark, and Murray Gell-Mann, the physicist who proposed them, just liked the sound of it.
It sounds like a duck with a speech impediment.
Yeah.
But these things are real.
They are very real. They are the fundamental constituents of matter. There are 6 flavors. Again, physicists being whimsical with the naming.
The flavors are great.
You have up, down, charmed, strange, top and bottom.
I'll have the strange soup, please.
Exactly. But for you and me, for the chair you're sitting on, for pretty much everything, we only really care about the up and down quarks.
So the other 4 are just exotic.
They're heavy, unstable, and they decay very quickly. We usually only see them for fractions of a second in particle accelerators, but a proton is just 2 up quarks and a down quark.
And neutron?
2 downs and an up. It's a simple recipe, but it builds everything.
Now, there is a detail in the research that I found genuinely confusing. It talks about color confinement.
Uh-huh.
It says quarks are never found alone. Why is that? Are they just incredibly social?
They're the ultimate introverts, actually. They refuse to be seen in public alone. This is due to the strong nuclear force.
The strongest of the 4 forces.
By far. Think of the bond between 2 quarks like a rubber band. If they are close together, the band is loose. There's not much tension.
Okay, standard rubber band physics. I'm with you.
But here's the twist. With a normal rubber band, eventually, if you pull hard enough, it snaps.
Right.
With quarks, as you pull them apart, you are pumping energy into that system, into that rubber band.
Okay.
And remember Einstein's famous equation?
E equals mc squared.
Energy equals mass. Eventually, you put so much energy into stretching that rubber band that the energy itself turns into new quarks.
But wait, so if I try to pull a quark out of a proton,
Yeah.
I don't get a free quark. I just create a new friend for it.
Precisely. The energy snaps and forms a new particle-antiparticle pair. So you never end up with one quark, you just end up with two groups of quarks. That's confinement.
And that's why things are solid.
It's the reason the universe is stable. If quarks could drift apart, protons would dissolve, atoms wouldn't exist, and we wouldn't be here having this conversation.
That is wild. The stability of my body relies on these things refusing to be single. Okay, so those are the quarks, but they aren't the only bricks.
Yeah.
You also have the leptons.
Correct. The most famous lepton is the electron. That's the little guy buzzing around the outside of the atom. It's responsible for electricity, chemistry.
The fact that I can't push my hand through this desk.
All of that. The repulsion between the electrons in your hand and the electrons in the desk.
But the lepton family has a black sheep, the neutrino.
The ghost particle.
The research mentions these things are passing through us right now.
In the billions, every second, trillions of neutrinos from the sun are streaming through the roof of your house, through your head, through your body, through the floor, and all the way through the earth and out the other side.
And they don't hit anything.
Almost never. To a neutrino, an atom is almost entirely empty space.
Wow.
They're electrically neutral, so they don't feel the electromagnetic force. They don't really feel the strong force. They just glide right through. You would need a block of lead, a light year thick, to have a 50-50 chance of stopping an average neutrino.
That gives me a bit of an existential crisis. I feel solid, but to a neutrino, I'm just a ghost.
To a neutrino, you are basically a vacuum.
Great. Okay, so we have the bricks. Quarks and leptons. Those are the fermions.
Nice.
But if I just dump a pile of bricks on the ground, they don't turn into a house. They need mortar. They need something to glue them together.
And this brings us to the other family, the bosons. In the standard model, matter particles, fermions, are the actors.
And bosons are the script.
Exactly. They tell the actors where to go and how to interact. They are the force carriers.
I used to think forces were just magic fields, like magnets just knew to repel each other. But you're saying they're actually throwing things at each other.
In a quantum sense, yes. When two magnets repel, they are exchanging streams of virtual photons. The photon is the carrier of the electromagnetic force.
The photon is a particle of light.
It is. The photon is the messenger saying, move away, or come closer.
So light, the thing we see, is just the visible part of electricity and magnetism.
It's all the same force. Then you have the gluon. Can you guess what that does?
I'm going to go out on a limb and say it. Glues things.
It glues quarks together. It carries the strong nuclear force we were just talking about. That rubber band is made of gluons.
Okay, that makes sense.
Then you have the W and Z bosons, which carry the weak nuclear force. That's responsible for certain types of radioactive decay.
And then the big one.
And finally, the celebrity of the group, the Higgs boson.
The God particle. I hate that name, by the way.
Physicists hate that name too, a publisher's gimmick. But the particle is crucial. The Higgs boson is an excitation of the Higgs field.
A field that's everywhere.
Think of the Higgs field like a cosmic molasses that fills the entire universe. As particles move through it, some of them get bogged down. That resistance, that is what we call mass.
So particles that interact a lot with the Higgs field are heavy, and particles that don't are light.
Exactly. The photon doesn't interact with it at all, so it has no mass and travels at the speed of light. The top quark interacts with it a lot, so it's incredibly heavy.
So without the Higgs, electrons would just zip around at light speed and never form atoms.
Everything would be zipping around at light speed. The universe would be a featureless soup of radiation. No mass, no atoms, no us.
Now, I want to pause on the forces for a second because there is something in the notes that I've always found baffling. We have 4 fundamental forces: strong, weak, electromagnetic, and gravity. And the notes say gravity is the weakest.
By far. It's not even a competition.
How can that be true? Gravity holds the planets in orbit. It crushes stars into black holes. It keeps me on the ground. It feels pretty strong when I fall off a ladder.
It feels strong because it is cumulative. You are feeling the gravity of every single atom in the entire Earth pulling on you at once.
Hmm.
All 6 trillion kilograms of it.
Okay.
But think about it this way. Take a little fridge magnet, a tiny magnet size of a coin. Put it on your fridge.
Right.
That magnet is holding itself up against the gravitational pull of the entire Earth.
Okay. When you put it that way.
One tiny magnet beats the whole planet. That shows you that electromagnetism is roughly 10 to the power of 36 times stronger than gravity.
That's a 1 with 36 zeros.
It's an absurdly big number. Gravity is incredibly weak, it just has a very long range, and it always adds up. It never repels.
And this is the problem with physics, right? Gravity is the odd one out.
It is the outlier. The Standard Model explains the other three forces perfectly using quantum mechanics. They all have a force carrier particle.
The gluon, the photon, the W and Z.
Right. But gravity refuses to fit in the equation. We have general relativity for gravity, which is Einstein's smooth, curved spacetime. And we have quantum mechanics for everything else, which is pixelated, jumpy particles.
And they don't play nicely together.
They do not get along. Finding a theory of quantum gravity is the holy grail of modern physics.
So the Standard Model is amazing, but it's technically incomplete because it's missing gravity.
Right. It's a map of the United States that is missing Florida. It's mostly right, but you're going to have problems if you try to drive to Miami.
Okay, so we have our ingredients, we have the bricks and the mortar, but now we have to go back to the beginning. We have this elaborate system of particles. How do we get them from nothing? This is where we have to talk about the mechanism.
And this is where we have to revisit that box you imagined earlier, the empty void.
Right. The research says, in modern physics, a vacuum is not empty.
It is a seething cauldron. This is a consequence of one of the weirdest and most powerful ideas in physics, the Heisenberg uncertainty principle.
Most people know this principle as you can't know the position and speed of a particle at the same time.
Correct. The more you pin down where it is, the less you know where it's going, and vice versa.
The act of measuring changes the result.
But there is another version of that equation. You cannot know the energy and the time of a system precisely.
What does that mean in English?
It means that for very, very short periods of time, the amount of energy in a vacuum can fluctuate wildly. The energy level isn't zero, it's fuzzy. It can spike.
So nature is allowed to cheat, as long as it's quick about it.
It's allowed to take out a loan. I love the bank loan analogy here. Imagine you have $0, but you can go to the bank and borrow $1 million,
Okay.
as long as you pay it back in 1 second.
So for 1 second, I'm a millionaire, but then it's gone.
Exactly. In the quantum vacuum, empty space can borrow energy from the future to create mass, because energy and mass are the same thing.
E equals mc squared again.
So, out of nowhere, a particle and its antiparticle pop into existence. They are the $1 million, but the debt has to be paid. So they almost immediately crash back together, annihilate, and disappear.
And this is happening everywhere, right now.
Everywhere, all the time, right in front of your nose. Space is bubbling with these virtual particles.
It sounds like magic. I appear, I disappear. How do we know this is real and not just, a mathematical quirk?
We can actually measure it. It's called the Casimir effect.
Okay.
If you take two metal plates and put them extremely close together in a perfect vacuum, so close that the bigger virtual particles can't fit between them.
Right, there's not enough room for them to pop into existence.
Precisely. But the virtual particles can still pop up on the outside of the plates. So you have more particles pushing on the outside of the plates than on the inside.
And the plates get pushed together.
They get pushed together by nothing, by the pressure of the vacuum itself. So we know the seething energy is real.
Okay, so we have this bubbling soup of potential. This nothing is actually full of activity. But how do we get a permanent universe out of it? If they always pay back the loan, shouldn't we still have nothing in the end?
Unless you can stop them from recombining. Unless you can rip the loan contract up before they pay it back.
How would you do that?
Well, the source gives us two ways to do that. One involves black holes Hawking radiation.
Right. Stephen Hawking's big idea.
Imagine a pair of these virtual particles popping up right on the event horizon, the edge of a black hole. One falls in, the other escapes.
So they can't recombine.
They're separated forever. The one that escapes becomes real. It becomes a permanent particle.
So the black hole pays the debt.
The black hole loses a tiny bit of mass to pay for the particle. That's why black holes aren't truly black. They glow faintly and, over trillions of years, evaporate.
And the second way, and this is the big one for us, is inflation. The idea that the very early universe expanded so fast that it literally ripped these virtual particles apart before they could annihilate.
Exactly. You stretch the space between them faster than the speed of light. They lose track of each other.
They're suddenly on opposite sides of the universe.
And they get locked into reality. The loan gets forgiven. The universe keeps the $1 million.
So if this theory is right, you and I and the listeners, we are basically just quantum fluctuations that got frozen into existence.
We are overextended loans that the universe never paid back.
That is philosophically heavy.
But let's put it on a timeline. We have the mechanism. Now let's watch the movie. Segment 3. The timeline of creation. 13.8 billion years ago.
The Big Bang.
Now, I feel like we need to clear up a misconception immediately. When I hear Big Bang, I think of a stick of dynamite going off in an empty room. Everyone does. It's a terrible name, really, but that is wrong. It wasn't an explosion in space. It was an explosion of space.
This is the hard part to wrap your head around. There was no outside for it to expand into.
Correct. The singularity, that tiny point of infinite density, contained all of space and time. When it started expanding, it wasn't expanding into a void. It was creating the void as it grew. Every point in space was the center of the explosion.
So time equals 0. We have the singularity. Then almost instantly we hit the inflationary epoch.
This is the crucial moment. We are talking roughly 10 to the power of minus 36 seconds after the start. An incomprehensibly small fraction of a second.
And in this fraction of a second, the universe grew.
How much? It expanded faster than the speed of light. It went from the size of a proton to the size of a grapefruit, or some say much, much larger in less than the blink of an eye.
Wait, hold on. Faster than the speed of light? I thought Einstein said that was illegal. Speed limit strictly enforced?
Einstein said nothing can travel through space faster than light. But space itself.
Space can do what it wants.
Space can do whatever it wants. It can expand at any speed. Imagine dots on the surface of a balloon. As you blow up the balloon, the dots move apart, but they aren't running across the rubber. The rubber itself is stretching.
Loophole. I love it. Okay, so why does this inflation matter? Why do we need it in the theory?
It solves two massive headaches for cosmologists, the horizon problem and the flatness problem.
Okay, let's take the horizon problem. The notes use a coffee analogy, which I like.
Imagine you have a cup of black coffee and you pour in some cold milk. It takes time for them to mix and become a uniform brown, right? You have to stir it.
Right. The heat and color have to spread out.
The universe is the same. When we look at the cosmic microwave background, the heat left over from the Big Bang, it is incredibly uniform. It's the same temperature everywhere, to within 1 part in 100,000.
So what's the problem with that?
So the observable universe is 93 billion light years wide. There hasn't been enough time since the Big Bang for light or heat to travel from one side to the other to equalize the temperature.
They're not in contact.
They've never been in causal contact. They shouldn't know the other exists. It's like two people on opposite sides of the earth waking up and deciding to wear the exact same outfit, down to the socks, without ever talking. It's deeply suspicious.
Unless they were together before they woke up.
Bingo. Inflation says everything was touching tiny and huddled together in thermal equilibrium long enough to get to the same temperature. Then zoom inflation ripped them apart instantly. So they are far apart now, but they match because they started together.
It solves the problem beautifully. And the flatness problem.
That's about geometry, the overall shape of the universe. It turns out that the density of the universe is incredibly close to a critical density.
What does that mean?
If the Big Bang had been slightly weaker, gravity would have crunched the universe back down instantly. A big crunch. If it had been slightly stronger, everything would have flown apart so fast, stars and galaxies could never form.
We are on a knife-edge balance.
An unbelievable knife edge. Inflation explains how we got balanced so perfectly. It stretched the universe out so much that it looks flat, just like the Earth looks flat when you're standing in a field in Kansas, even though it's a sphere.
It smoothed out all the wrinkles. Okay, so inflation ends. The universe is still expanding, but now it's slowing down a bit. What is it like out there?
It is hell. It is the primordial soup. We are talking trillions upon trillions of degrees. It is too hot for atoms. It's even too hot for protons and neutrons.
So what is it?
It is just a quark-gluon plasma.
This is the soup before the ingredients clumped. Quarks and gluons just floating around.
Right. Quarks are swimming around freely because the energy is so high that the rubber bands of strong force are all loose and floppy. It's pure chaos.
Then, as the universe expands, it cools, and we get something called symmetry breaking.
This is a fancy term for freezing. Think about water. Liquid water looks the same in every direction. It's symmetrical. But if you freeze it, it turns into ice crystals.
The crystals have a shape, a structure.
They pick a direction, they break the symmetry. At the very beginning, we think all the forces of nature were one single superforce.
They were all symmetrical.
Exactly. As the universe cooled, they froze out, one by one. Gravity split off first, then the strong force. Then the electro-weak force split into electromagnetism and the weak force. As they split, the universe took on the properties we know today.
And once the strong force separates, it clamps down.
The rubber bands snap shut. This is the Hadron Epoch. We're talking microseconds after the Big Bang. Quarks get pulled together in threes to form protons and neutrons for the first time.
So now we have the nuclei of future atoms, but we don't have atoms yet.
Not yet, still way too hot. We enter Big Bang nucleosynthesis. This lasts for about 3 to 20 minutes. The whole universe is one giant nuclear fusion
The
reactor.
protons are smashing into neutrons.
And they're making the first atomic nuclei, mostly hydrogen, which is just a proton, and helium, which is 2 protons and 2 neutrons.
And that's it, just hydrogen and helium.
And a tiny, tiny pinch of lithium. That's all you get in the Big Bang. Every other element, the carbon in your body, the oxygen you're breathing, the iron in your blood, that had to be cooked billions of years later inside stars. The Big Bang only gave us the gas.
So we have this hot gas, this plasma of nuclei and electrons, but it's still foggy, right?
It is completely opaque. It's a plasma. The free-roaming electrons are still too hot and energetic to settle down. They're buzzing around, crashing into photons.
So light can't travel.
Light can't travel more than a tiny distance before hitting an electron and getting scattered. If you were there, you wouldn't see anything. It would just be a glowing white fog in every direction.
For how long does this go on?
A long time, 380,000 years.
Wow, so for almost 400,000 years, the entire universe was a glowing fog bank.
And then we hit the moment of recombination. The universe cools down to about 3,000 degrees Kelvin. That's about the temperature of the surface of a cool star.
And that's the magic temperature.
That's cool enough for the protons and helium nuclei to finally capture the electrons.
The electrons get trapped in orbit around the nuclei.
They form the first neutral atoms, and suddenly the fog lifts, the electrons aren't bouncing around anymore, scattering light. The photons are free to travel unimpeded across the universe.
That'd be light.
Literally, the universe becomes transparent, and that light, released 380,000 years after the Big Bang, is still traveling today.
Which is the perfect segue to segment 4, the evidence. Because everything we just said sounds like a fantastic story.
It does.
But this isn't science fiction. We need proof. And the biggest piece of proof is that light you just mentioned.
The cosmic microwave background, the CMB.
The story of how this was discovered is one of my favorites in all of science. It involves 2 guys, a giant radio antenna, and pigeon poop.
Arno Penzias and Robert Wilson, 1965. They were working at Bell Labs in New Jersey. They had this massive horn antenna, and they were trying to do some radio astronomy, but they had a problem.
A hum, a noise in the data.
A persistent low-level hiss. Static. It was there day and night. It was there no matter where they pointed the antenna.
So they thought it was a technical glitch.
They thought it was interference from New York City. They thought it was the military. They thought their equipment was faulty.
They checked everything.
They checked the wiring. They recalibrated everything. They taped over rivets. And yes, they noticed a pair of pigeons had been nesting in the antenna and leaving deposits.
White dielectric material, as they politely called it in the paper.
The politest term for bird poop in scientific history.
So they scrubbed the pigeon poop, they caught the pigeons, and mailed them to another facility.
They evicted the pigeons, but the pigeons came back, so they took more permanent measures. But the hum was still there.
And at the same time, not far away.
Just down the road at Princeton, a team of theorists led by Robert Dicke was predicting that if the Big Bang theory was right, there should be a leftover glow. A background radiation from the early universe cooled down to about 3 degrees above absolute zero.
And Penzias and Wilson were listening to it. By accident.
They were listening to the sound of the creation of the universe, and they thought it was bird droppings. They eventually connected with the Princeton team and realized what they'd found. They won the Nobel Prize for it.
That hiss is the CMB. It is the oldest light in the universe. And when we map it with satellites like COBE and WMAP, it matches the predictions perfectly.
But perfectly. It shows us exactly what the universe looked like at 380,000 years old. And you can see in the map the tiny fluctuations, the tiny temperature differences that were the seeds stretched out by inflation that later grew into all the galaxies and clusters of galaxies.
What other evidence do we have?
Redshift. This goes back to Edwin Hubble in the 1920s. He looked at distant galaxies and realized their light was shifted toward the red end of the spectrum.
This is the Doppler effect, right? Like an ambulance siren.
Exactly. When an ambulance comes toward you, the sound waves get squished together and the pitch goes up, high pitch. When it drives away, the waves get stretched out and the pitch drops, low pitch.
And light does the same thing.
Light does the same thing. If a galaxy is moving away from us, its light waves get stretched out. Blue light becomes red light. We call it redshift.
And Hubble saw that everything was red.
Almost everything. And crucially, the farther away it was, the redder it was.
So the farther galaxies are moving away faster.
Which meant the universe is expanding. And if it's expanding logically, if you rewind the tape, it must have been smaller in the past.
All the way back to a single point.
Correct. The third pillar of evidence is the abundance of elements. The Big Bang Theory and its nuclear physics predict a very specific recipe for the early universe. About 75% hydrogen, 25% helium.
And when we look out there,
When we look at the oldest gas clouds in the universe, pristine clouds that haven't been touched by stars yet, that is exactly what we find. The math matches the reality to a T.
it's amazing that we can figure all this out from here. But, and there is always a but in science, we don't know everything.
Not by a long shot.
In fact, the source makes it clear that we actually know very, very little. We call this the dark sector.
This is the humbling part of cosmology. Everything we have talked about. Quarks, electrons, stars, gas, you, me, that is baryonic matter. Normal stuff.
And that makes up,
Well, about 5% of the total mass and energy content of the universe.
5%. So if the universe is a pie, we are just the crumbs on the plate.
We are the cherry on top of a cake made of invisible stuff we don't understand. The other 95% is dark matter and dark energy.
We need to distinguish these because I think people use them interchangeably. Dark matter is the glue, right?
Right. Dark matter makes up about 27% of the universe. We can't see it. It doesn't emit light. It doesn't reflect light. It doesn't interact with light at all.
So how do we know it's there?
We know it's there because of gravity.
This is the galaxy spin problem.
Vera Rubin noticed this in the 1970s. She looked at how galaxies spin, and they spin fast, really fast, so fast that based on the visible stars and gas, there isn't nearly enough gravity to hold them together.
They should fly apart.
They should fly apart like a vaguely constructed merry-go-round. But they don't. Something invisible, some extra mass, is providing the gravitational glue to hold them together.
An invisible scaffold that galaxies are built on.
We call it dark matter. We think it's some kind of new undiscovered particle, maybe a WIMP, weakly interacting massive particle. But we haven't caught one yet in any of our detectors.
And dark energy.
Dark energy is the opposite. It's the pusher. It makes up the lion's share, about 68% of the universe.
And this is related to the expansion speeding up.
Yes. For a long time, everyone thought the expansion of the universe would slow down over time. Gravity should pull everything back. We might even end in a big crunch.
But we aren't slowing down.
In 1998, two teams of astronomers were looking at distant supernovas to measure the rate of deceleration, and they found, to their complete shock, that it's not decelerating.
It's accelerating.
The expansion of the universe is speeding up. The universe is putting its foot on the gas. Something is pushing space itself apart, overwhelming gravity on the largest scales. We have no idea what it is, so we call it dark energy.
So the future of the universe isn't a crunch. It's a rip.
Likely a big freeze or a big rip. Everything will eventually be pushed so far apart that we won't be able to see any other galaxies. The night sky will go dark except for our own local group. It's a lonely future.
Well, that's cheerful. Let's talk about one more missing piece before we get too depressed. Antimatter. The source calls this the baryon asymmetry problem.
This is the mystery of why we exist at all.
Because matter has an evil twin.
A mirror twin, antimatter. Every particle has an antiparticle with the opposite charge. The electron has the positron. The proton has the antiproton.
And if they meet,
They annihilate. They turn into pure energy, a flash of gamma rays.
the problem is that the Big Bang, with its E equals mc squared, should have made equal amounts of both.
Symmetry says it should be 50-50. For every quark, you get an antiquark. But if the Big Bang made 50% matter and 50% antimatter, they would have all mixed, annihilated, and the universe would just be a bland, boring bath of photons. No stars, no atoms, no us.
But clearly, matter won. We're here.
Matter won. There must have been a tiny imbalance. We think for every billion particles of antimatter, there were 1,000,000,001 particles of matter.
So a billion pairs killed each other in a huge flash of light.
And that one lonely survivor in a billion is what makes up all the stars and galaxies and people we see today. We are the lucky leftovers of a great annihilation.
We are the one in a billion. That makes me feel a little better about the whole Big Rip thing. So how do we solve these mysteries? We build giant machines. Segment 6, the tools of discovery.
The cathedrals of science. Particle accelerators.
The Large Hadron Collider at CERN, the LHC. It's the biggest machine humans have ever built.
It is a beast. 27 kilometers, that's 17 miles in circumference, buried 100 meters underground on the French-Swiss border.
How does it basically work? What are we doing down there?
It's a racetrack for protons. They use thousands of superconducting magnets cooled with liquid helium to be colder than outer space to steer two beams of protons in a circle in opposite directions.
And you make them go faster and faster.
They kick them with powerful electric fields on each lap until they are going 99.9999991% the speed of light.
And then you cross the streams?
You cross the streams, you smash them head-on inside giant detectors. At the collision point, the energy density is so high that it momentarily recreates the conditions of the universe a tiny fraction of a second after the Big Bang.
It's a time machine.
It really is. We are briefly melting the vacuum to see what strange new particles pop out of the seething cauldron. That's how we found the Higgs boson in 2012. We smashed protons together hard enough to shake the Higgs field and make a Higgs particle pop out.
Now, I know what some listeners are thinking.
Yeah.
Cool, you found a boson. Why should I care? How does this multi-billion-dollar machine help me?
It's the classic question. Basic research versus applied research. But the spin-offs from this kind of fundamental science are massive.
The source mentions medicine, for example.
Proton therapy. We use particle accelerator beams to treat certain kinds of cancer. Because we learned how to steer protons with incredible precision at CERN, we can now steer them into a tumor to kill it without damaging the healthy brain tissue around it.
And PET scans, I've heard of those.
PET stands for positron emission tomography. Positron. That is antimatter. When you get a PET scan, doctors are literally injecting you with a substance that emits antimatter, and they're using the annihilation signals inside your body to find disease. That is pure particle physics saving lives.
And the big one, the reason you are probably listening to this right now.
The World Wide Web. Tim Berners-Lee invented the web at CERN in 1989, not to sell shoes or watch cat videos, but to allow thousands of physicists all over the world to share the massive amounts of data coming from these experiments.
So the entire internet as we know it is a byproduct of hunting for quarks.
It's the ultimate ripple effect. We tried to find the start of the universe, and we accidentally invented the information age.
It just shows that you never know where curiosity will lead.
Never.
So we have covered the ingredients, the mechanism of the vacuum, the timeline of the Big Bang, the evidence, the dark sector, and the machines. It has been a marathon.
We covered 13.8 billion years in about an hour. Not bad.
As we wrap up, I want to go back to that philosophical note we started on. We started with nothing, and we found out nothing is actually a seething cauldron of potential.
It really blurs the line, doesn't it? Science can explain the how. We can tell you about inflation and quarks and symmetry breaking, but the why remains elusive. Why is there a quantum vacuum in the first place? Why are the laws of physics tuned exactly this way?
This is the fine-tuning problem. If the strong force had been just 1% weaker,
No atoms would form. If gravity was slightly stronger, the universe would have collapsed back on itself before life ever began. It feels, to some people, like the universe knew we were coming.
or maybe there are infinite universes, and we just happen to live in the one that works, the one where the lottery numbers came up.
The multiverse theory. That is a deep dive for another day, for sure.
It is. But it leaves us with a sense of awe, and also a sense of responsibility. The source touches on this, the ethics of knowledge. We are unlocking the source code of reality.
We are. And that power can be used for PET scans and the internet, or it can be used for destruction. Understanding the atom gave us nuclear power and nuclear weapons. We have to be wise with what we find.
So here is the final thought I want to leave everyone with. If particles arise from this boundless reservoir of possibility, those quantum fluctuations, and that reservoir is everywhere, right in front of your face, is the universe still being created right now?
In every cubic centimeter of space, virtual particles are popping in and out of existence. The potential for creation is always there. The Big Bang might be over, but the mechanism that made it It's still humming in the background of reality.
It makes you look at the empty air a little differently.
It certainly does.
We want to hear from you. Does the idea of a seething vacuum make sense to you, or does it sound like we've completely lost our minds? How do you visualize the start of it all?
We'd love to read your theories.
Thanks for diving deep with us into the void. Until next time, keep looking up and keep looking in.
Stay curious.